And Gabe, right? How you doing, sir? Good. A few more minutes and then we'll get started. So, you guys have got me here, any questions at all on any of the stuff that we've gone over? Okay. I was hoping, I don't know if Vaughn is going to be here at all today. I haven't heard from her. So Vaughn Benson is another flight instructor, and she's going to get each of you signed up for the Young Eagles program, which in turn will get you the Sporties private pilot program. It's like $300 for free. It's just included with it. And it follows along with what we cover in the book. It's just another set of materials. They've got really good quizzes on there. It's just really nice material. So if she does come in, what we'll do is we'll have you guys come out, we'll visit with her for a second. She'll get you registered for Young Eagles, and then you'll get this Sporties free Sporties program. So and like I said, you could use it along with the SIA material if you want. So it's just another tool to help you understand some stuff. And then next week, Ethan's dad, if he's still planning on doing this, was going to come in. Ethan's dad, Weston, is it Paper? Yeah. Paper is a American Airlines. And he's also, correct me if I'm wrong on this, but he was a wing commander, right, in Madison. Okay, yeah. So he was military aviation. Yeah, so he's going to come in. So he'll be answering any of your questions and things like that. Aviation, commercial aviation, things like that, and then also military aviation. So, morning. And what is your name?
Traven.
Traven. Okay, yes, okay. Yeah, you've been watching online, Traven?
Yep.
Yep. Do you have a kit? Okay. Okay. There you go, sir. Thank you. All right. And I think we'll just go ahead and get started. So let's hold that thought. I don't have anybody else. No. All right. So we're going to be going through chapter 4 this week. Principles of flight. We're probably going to get into chapter 5. Chapter 4 is fairly short, but it's got some pretty complex stuff that we're going to need to understand before we move on to chapter 5. So if you want to put your books to that, it's 4-1 or 2 actually to start on. So. And actually, let's do just for like 5 minutes, let's just do a quick review of what we talked about last week before we dive into this. So I want to bring up our simulation here. Okay. So do you see those surfaces that are moving on the plane there? Does anybody know what those are? Ailerons. Okay, what about these surfaces right here? Moving. Flaps. Those are called the flaps. Once they both work together. Okay, how about this one right here? What's that called? Yep. Okay. This right here. Yeah. Okay. Perfect. All right. Good. And does anybody remember the different parts of the aircraft there? Okay, so let's actually go right here. Let's do this. What's that? Power plant nose. Yep. Okay. Then obviously you probably know what this is right here. Yeah. And then this whole area right here. Yep. And then this right here. Empennage. Right. All right? We didn't talk about too much other than that. So that's we got obviously the tricycle landing gear. We talked a little bit about that. For bonus points, does anybody know what conventional gear aircraft looks like, or one distinctive factor of conventional gear?
Instead of having the third wheel on the front, it's on the back.
Yeah. This is a tricycle gear aircraft, and you know that because the gear is in the front. What Donnie says is for a conventional gear aircraft, the gear is in the back. It's usually like a little tire like this. You don't have the gear up here, which you'll see in tail. We call them tail draggers. That's a term for them. But usually what they'll do is they'll move the tires up front instead of having them back here. They'll move the tires or the landing gear closer up front. So you've got you're there, you're right there. So that's essentially what a conventional gear aircraft is like. So again, tricycle gear aircraft is going to be something like that there. Okay. All right. Gosh, there's really much anything else that we talked about. Oh well, let's do this. Okay, so what is? Let's see. Let's do it. Just this here. So, do their axes of flight. So what is this axis right here? Vertical axis. Excellent. Okay. How about this one?
Pitch.
So we got pitch, we've got longitudinal, we've got latitudinal. How many say latitudinal? Raise your hands. Okay. How many say longitudinal? We got one. Okay. Two, 3. And then how many say pitch? So it's actually the longitudinal axis, but that's the plane pitches on that axis. It doesn't pitch around that axis. That's the axis that moves up and down and pitch. So okay, so latitudinal, and then so there's 3 different types of movement of the aircraft. Does anybody know what they are? The different ways that it moves? Pitch, roll, and yaw. Okay, so this is what? Roll. Yep. Okay. And this is pitch. Okay. And then this right here. Yaw. Okay. So yaw rolls around what axis? Vertical axis. Okay. So if this is the vertical axis right here, right? The aircraft yaws around that axis. Okay. So the latitudinal axis, can you guess which is it? Is it pitch or, okay, got it. Yep. Pitch. Rolls around that axis right there. So that's this right here, my finger is the axis, and the plane rolls around that axis. Okay. And then longitudinal, what's that? Roll. Yep, it rolls this way. Got it. Okay, good. All right. Enough for the review there. So let's dive back into our starting out today with. Okay, so principles of flight. So let's first let's talk about a little bit about so we're going to talk a little bit about a lot about air and what it is, what the qualities of. So you don't think about this, but air is actually a fluid. Okay, it flows, and it has weight to it. You don't think about that either. Does anybody know how much a column of air weighs? Like it's a square inch of air would weigh if we were to actually weigh it. I'll give you a hint. You hear it occasionally in physics. You'll hear the term PSI, which stands for pounds per square inch. Is that what you say? 15? Did you say 15 or 15? Okay. So you said about 5 to 10. Okay. It's actually about, you're close, 14.7 pounds per square inch. If I were to take, so this is hard to understand because we're living in all this air is, we're at the, down here on Earth, and we're used to the atmospheric pressure, which is roughly 14.7 pounds per square inch that's acting on the body, right? So if I were to take a column on here that's essentially a square inch, and we're, fill it with air, and then just hold it in my hand, I would feel 14.7 pounds per square inch on the hand. And of course, I can't feel that because we're already feeling it all around our bodies right now. But if we were to weigh it, it would be 14 pounds per square inch. So air is a fluid, and it has weight. The further you go up, so let's say, let's go up to 30,000 feet. Let's take that same column of air that's in this tube of, a quarter inch, let's say. Let's go to 30,000 feet. Is that air going to, if we weigh it up there, is it going to be heavier or lighter?
Lighter.
It's going to be lighter. Yeah, definitely. Okay, and we go further up, it's going to be even lighter. Okay, that should tell you something. That's something we're going to apply a lot in aviation. We're going to use that, especially when we start getting into altimeters, and talking about atmospheric pressure and stuff like that. It all relates to that, the pressure that we're feeling down here. So, okay, so air is a fluid, and it has weight. So there's, they talk about in the book, they talk about viscosity. You're never going to see that on the written test. I don't even know if you'll see it on the commercial test, to be honest. But we do want to talk about it because the viscosity does play into aerodynamics. So when we think of molasses, we think of a slow-moving fluid, just like air. Air has a viscosity, but it flows fast. Or another one to use would be water. So if we had like water, for instance, we pour it down ramp, it's going to go relatively fast down that ramp. If we pour syrup down it or oil, it's going to go a lot slower. Okay, so a high viscosity fluid is going to be like syrup or oil. A low viscosity fluid is going to be like water or something thin like alcohol or something like that. It's going to be very thin. So that's the difference between low viscosity and high viscosity. So again, they go in through it there. There's also what we call friction. If you were to take a bottle of molasses and pour it over a very smooth, like a mirror, for instance, that's slanted down like this, it's going to flow fairly smoothly. But if I take that same molasses and pour it down a mirror that's covered in sandpaper or something like that, it's going to take a lot longer to flow down there. That's friction. Okay, so and same with water. Yep.
And also referred to as drag, right?
What's that?
Also referred to as drag, right?
Drag.
Drag.
Well, yeah. I mean, you could call it drag. Yeah. It actually, that gets more into you're jumping more into parasitic drag now, which we're going to get into. I don't want to get in. Sorry, guys. I got to this one. There we go. Okay. Yeah. So there is drag on it. Yes, and I wasn't thinking about it in terms of that, but it essentially is drag. It's what we would consider parasitic drag on there. Okay. But the rest of you don't worry about it. We're going to get into that later on. So, all right. So again, even what looks like a smooth surface is going to have some, of that the roughness to it. So here's a typical, aircraft wing here. You can see all these little lines on it. These are like the rivet lines. So this would be like an aluminum aircraft. And you can see all these little lines on it. Those would be the rivets and stuff like that. So those all create drag or friction. They're all going to create some sort of friction in the aircraft. So some airplanes like the Cirrus, they're made of composite materials and there's no rivets on them. So what you're going to see is a nice smooth surface. So the air is going to flow over that a lot smoother. There's not going to be any resistance to it. Okay. All right. Let's see here. And then, okay, so this is on the next page, 4-3, atmospheric pressure. So we've talked a little bit about that. So there is what's called a standard atmosphere. This is something, again, you're going to want to know. You're going to see a ton of questions on this on the FAA written test. And essentially, what a standard atmosphere is, it's a way for us as engineers, as pilots, or whatever, to communicate performance figures. We don't know because the atmospheric pressure changes from one place to the next. If I go drive over to Bearwood, the pressure there is going to be slightly different again because you got changes in the atmosphere and the temperature. They all affect atmospheric pressure. Okay. Now, have you ever looked at like a weather map and you've seen those little isogonic lines and they show like the pressure, on it, like 2 point or 29.8 or something like that. They'll have those. They're actually talking about air pressure at that station. So just see here. Maybe I can bring one up here. Give me a second here. I'm just going to see if I can bring up another map here. Here. And we have no weather. That's unusual. Usually have some. So here we go. Okay. So there's two different ways that we measure atmospheric pressure. Two different units that we can use to measure it. One is inches of mercury, and you've probably heard this. A barometer has mercury in it, right? And what does a barometer do? It measures the pressure in the atmosphere. So if I'm down here on the ground, it's going to be somewhere around 29.92 inches of mercury. It could be as high as 31 point something and as low as 28, which would be really low. And we're going to discuss that here in a second, how that works. But what these little isogonic lines do here is they show us the temperature, or the inches of mercury. In this case, they also measure it. So there's inches of mercury, but it can also be measured in hectopascals. And that's what this is right here. Let's see if we can zoom in this. Okay, so you see this right here, 1018. That's the hectopascals for that line right there, and that translates to something in inches of mercury. I don't know what it is off the top of my head there, but then here looks like it's going down. So we've got 1018, 1016, 1014. So we can see that we're starting to go from high pressure here, just north of Minnesota, and into Canada. The pressure is starting to go down, and then it goes down like here. It's just 1004 hectopascals. And again, normally we show that in inches of mercury, but the international measurement for pressure is hectopascal. So the United States is a little different. We do it in inches of mercury, but it gives you the same information. What this is telling us is that there's relatively high pressure here, and then it starts going down as we go further west into lower pressure right here. And notice the lowest pressure right here is. The lowest pressure is right here, right around there. Oh, there's the low pressure right there, 995 hectopascals. And that's low. And notice all the bad weather around that low pressure system. Typically, whenever you see low pressure on a map, it's going to include bad weather. It's just what low pressure does. It basically brings in moisture, humidity, or whatever, and it creates energy for the atmosphere to produce bad weather. And that's what we're seeing here. So if I look at a map and all I see is highs and lows, I can pretty much tell you where the bad weather is going to be at just by looking at where the lows are. A high pressure, again, don't see much for bad weather out here. That's a high right there. There's another high, and again, there's no bad weather over there. That's not always the case, but for the most part, when you have a low pressure system and a high pressure system nearby, there's always going to be some bad weather there. There's other things that are involved in it. Obviously, you have to have moisture to produce that energy to produce bad weather. And we'll get it. We're going to study weather theory in another chapter here, so I won't go into it. But, and these measurements are all on the ground. So in other words, if this pressure hectopascal measurement was made by either an observation station or was calculated through a computer model to calculate the pressure on the surface of the planet, that's what that represents there. Not at 10,000 or 20,000 or 30,000. That would be a totally different pressure. Okay, so now let's go back to our thing. Now this is where it gets interesting. This is what we're gonna dive into, and hopefully some of you may get this right away and others may not. It's okay if you don't understand this right now, but by the time you're done with the class, you really need to have this concept down. So let's talk about atmospheric pressure. So the way a barometer works, this right here is a container for the mercury right here. This area right here is a container, right? And it's just like a beaker or something like that. In that beaker, you can see that there is a okay, you can see there's a fluid inside this container, and they've cut away this little chunk of the container so you can actually see inside there. And then in the container of mercury, you've got a tube that's open down here at the base of the container, so the fluid can move up through that. And then there's a tube that goes up, and it's sealed at the top. So this is a basic barometer, and this is what they learned a long time ago, that they could monitor how far up that mercury moved to, see if we had relatively high pressure in the atmosphere or relatively low atmosphere. So remember I was talking about hectopascals and millibars. So that this is the two different forms of measurement. So you've got the 29.92 inches of mercury, and in this case it's in millibars, hectopascals. So here on this side, so you've got the measurement. So this is essentially 29.5 inches of mercury that the atmosphere is pushing down on it. So let's back up a second. So as the outside air, if let's say we sit here, okay, and we have a device like this set up, and we have a high pressure system move into this area, what is that going to do to this mercury? What is it going to do to the column of mercury in this sealed tube? And again, we're starting out with low pressure, and then we've got relatively high pressure moving into the area. What is it going to do to our barometer? Is it going to increase that mercury or decrease the mercury? It's going to increase it. Now, why does it increase it? Yeah, it's putting pressure on this open pool of mercury. It's forcing it to go up higher. This is an important concept, and you definitely want to understand this. Because later on we're going to get into aerodynamics and then weather theory and things like that. We're going to be discussing how this stuff works, why it works the way it does. So, and conversely, if we go from an area of high pressure, let's say there's a low pressure system out in Minnesota and it's moving our way, which it oftentimes does. So let's say it moves in here, what's going to happen to the column of mercury as that low pressure centers over the top of us? It's going to drop, right? Exactly, because there's less pressure on this outside pool of mercury. So that's going to drop, and we'll have like 29.9 inches of mercury or something like that showing in the barometer. Okay. All right. What would happen if I were to take this barometer that's now reading 29.92, let's say, and I were to take it up to 30,000 feet? Is it going to go up or down? It's going to drop. Everybody says it's dropping. Okay, it makes sense, right? Because there's less atmospheric pressure up there. So the air is less dense. There's less pressure up there, and so this is going to drop. Okay. All right. I think we got that. Any questions on that so far? Good. Okay. All right. So standard atmosphere. So the standard atmosphere is 59 inches. I'm sorry, 59 degrees Fahrenheit or 15 degrees Celsius. And you're going to hear in aviation, you're going to hear us switch back and forth between Fahrenheit and Celsius. That's because the international standard for temperature measurement is Celsius. You go to any other country and they all use Celsius. We're one of the few countries that uses Fahrenheit yet. So you have to get somewhat, you have to understand, you know, the relationship between Fahrenheit and Celsius. At Celsius 0, that is 32 degrees or freezing. So 0 Celsius is freezing, 32 degrees Fahrenheit is freezing. Boiling at Celsius is what? Does anybody know? 100 degrees. Okay, you guys got it. Okay. And I can see why they use Celsius, but we never switched it off. So again, standard atmosphere is 59 degrees Fahrenheit, 15 degrees Celsius, and a standard pressure with standard atmosphere is 29.92 inches of mercury. So that's standard atmosphere. Whenever a pilot says what standard atmosphere, it's just should be 29.92 inches of mercury. That's what it is. That's a standard we have. And again, that's called collectively, the temperature and the pressure are called standard atmosphere, and it's again 15 degrees Celsius and 29.92 inches of mercury. That's a standard atmosphere. So there is a thing called lapse rate, and what the lapse rate is, and you're going to hear this used a lot, because in aviation we're not just on the ground, we climb up into the air, so there's a change in the atmosphere as you climb or descend. All right, so as we climb, the air becomes less dense. That becomes, does anybody know what happens to air as we climb? Is the air going to get warmer or cooler? Cooler. Okay, well, you guys really know your stuff. All right, so the air is going to get cooler as you climb, and that makes sense, right? Well, it may not, but I mean, if you go up to space, it's like, you know, absolute zero, right? It's really cold up there. I shouldn't say absolute zero. I mean, there can be some heat up there, but generally it's going to be, you know, very, very cold. And that makes sense. As you rise, you're getting close to that cold air. So it doesn't do it smoothly. There's, you know, different portions of the atmosphere that we're going to get into in another theory, like the troposphere, tropopause, stratosphere, stratopause, and things like that. And again, you don't have to worry about that right now. We're going to deal with that later on. But for lapse rate, that is what we really want to talk about with lapse rate is the change, the standard change in temperature and pressure as you climb. So this next thing here, let's see. So on your books, you can see this too. There's the standard atmosphere at sea level. So right now we're about 900 feet above sea level. So our standard temperature or standard atmosphere is, you know, for Reedsburg is going to be in the 28.86 and 13 degrees Celsius or 55 degrees. That would be a standard atmosphere. That's not what it is out today because it's non-standard out there. It's, you know, and again, you will very rarely go to an airport and find what's called a standard atmosphere, 15 degrees and 29.92 inches. It just doesn't exist very often. But we need to have that standard so that we can communicate these you know, tables and do formulas for the performance of the aircraft. But here we start out at sea level. So let's say we're at New York, you know, we're at sea level. So a standard atmosphere there is going to again be 29.92 and 15 degrees Celsius. If we go up 1,000 feet at New York, the pressure is going to what? Increase or decrease? It's going to decrease, yeah. And you look at it, if you go down and look at the altitudes here, all the way up to 20,000. Here we are at 13 inches for the pressure. For our inches of mercury that we're talking about atmospheric pressure, the barometer would be reading 13.74 inches for a standard day, that is. Okay. And then for the standard temperature up there, it's going to be about, you know, roughly 24.6 degrees Celsius. So these are important. There's, if you look at the, like from 29 to 28, it's roughly an inch of pressure. So that would be our lapse rate. So these lapse rates are pretty standard. So it's roughly, what is it, 90.94, roughly about an inch per 1,000 feet there. So you can see here 29 inches, 28 inches, 27, 26, 25. So it's roughly about an inch every 1,000 feet that you go up that you're going to see decrease in pressure. That's not so important. We'll get into some of that stuff later on when we get into performance right now. But you will see a decrease in temperature. And this is, again, we'll apply this in weather theory when we get into that. So the standard lapse rate is roughly 2 degrees Celsius here. So you can see at sea level, its standard temperature is 15 degrees. You go up 1,000 feet, it's now 2 degrees less. Because again, as air rises, it gets cooler. So we're dropping down 2 degrees, and you can see it just keeps dropping down roughly 2 degrees per 1,000 feet. So that's the standard lapse rate, is 2 degrees, okay, for temperature. And the standard lapse rate for pressure is 1 inch of mercury. Okay, that's the lapse rate. Talks about the change as you climb or descend. And normally we're concerned about the lapse rate as we climb, because if we're going up to really thin air, the performance of the airplane is it's not going to perform as well, just like we would. Okay, so let's talk a little bit about engines. So engines, in order for an engine to work, it needs fuel, it needs spark, and it needs air. Yep. Just see here. Okay, I just want to make sure that we're good here. Okay, so it needs air to breathe, just like we do. We need air to breathe. An engine needs air to breathe as well. Brings air into the cylinder, it burns that air, expels it. So as you go higher, there's less and less air. So a typical engine, aircraft engine, is going to lose power the higher you go, because there's less air up there. So that's one of the reasons why we need to know tables that we have to understand. You don't have to remember these numbers. You just have to know that, every 1,000 feet, you're going to lose about an inch of pressure, and you're going to drop in temperature by about 2 degrees. That's the lapse rate. Okay. That's something you will want to understand, and you definitely want to know this first one up here. So like here, this right here is something you're going to want to know there, that the 29.92 and 15 degrees Celsius. And you can remember, if you remember 59 degrees Fahrenheit, that's fine. You can always convert Celsius to Fahrenheit. I don't know if you know this, but on your E6B, it's got a nice little scale on it that converts Celsius to Fahrenheit. So if you know what Celsius is, you can always convert to Fahrenheit. All right. So I'm going to just show you a couple other diagrams here. So there's we've got airspeed of about 10 knots. We're going to have relatively low dynamic pressure on the hand. So if you've got air blowing on it like this, it's going to be, you're going to feel relatively low dynamic pressure. Here, 40 knots, now it's a lot faster, and it's hitting our hand, and now it's relatively high dynamic pressure. And then we've got 40 knots here, low air density. Okay, so the air is not as dense and low dynamic pressure. So it's not, because the air is not as dense, it's going to be a little bit less pressure there. So don't worry too much about that stuff. Let's talk a little bit about removing. So on 4.4, oh yeah, they still have got. Let's just cover these things real quick, and then we'll get into Newton and Bernoulli, and then we'll take a break, and then we'll talk about basic aerodynamics there. So there's a term called pressure altitude that you're going to hear a lot. We use this when we do aircraft performance calculations on there. So let's see if I've got one here. They don't have anything there. All right, so pressure altitude. In the book, it says pressure altitude is the height above a standard datum plane. Okay, that would be, our standard atmosphere of 29.92. This right here. So this is our standard atmosphere at sea level. That is right there. So pressure altitude is the height above a standard datum plane, which is a theoretical level where the weight of the atmosphere is 29.92 as measured by a barometer. So we're going to dive into this. I don't want to get into this too much because it's like almost too much to present to you right now. We're going to get into this into aircraft performance. You just need to know that pressure altitude is an important calculation when we're doing a long. It's not a problem if you're doing a short flight. If I'm flying from here to like Madison or something like that, I'm not so concerned about pressure, especially if you do the flight a lot and you're comfortable with the area. Pressure altitude isn't that a big of a concern. But if I'm flying across country, I want to know how well my aircraft is going to perform. And then I need to know these calculations. I need to know what this pressure altitude is and how well my plane is going to perform if I'm doing a long flight. Density altitude, now that one is basically it's here, let's just read it from the book. It's the standard datum plane, which again is the 29.92 standard atmosphere, 29.92 and 15 degrees is a theoretical pressure altitude, but aircraft operate non-standard atmosphere. Okay, so it's density altitude takes into account the changes in our atmosphere. Again, standard, we hardly ever come across a standard atmosphere. Like right now, we're in non-standard atmosphere. If I go outside, they measure the barometer, check the barometer, and check the temperature, it's not going to be the standard, atmosphere. It's going to be something different. So what density altitude does is it's basically a theoretical altitude that the plane would operate at if you were to take the temperature and the non-standard pressure of the atmosphere, and then it calculates an altitude. And again, this is going to make more sense when we actually start doing calculations, when we dive into calculations, for performance of the aircraft. But the thing that you need to know on the test, it's going to ask you, does temperature affect density altitude? You're going to say yes, it does. That's something that you need to know, understand that temperature affects density altitude. Well, let's go back a step. We talked about pressure as you rise, climb in an aircraft. We're climbing up into lower pressure, generally speaking, right? So if it's a standard atmosphere, as the plane climbs, the pressure is going to decrease, right? What's going to happen to the temperature? It's going to decrease, right? Okay, so as I climb, we're going to climb up into cooler air, generally speaking. Now, there are times we have what's called temperature inversions, where when you climb up, you're actually going to be climbing up into warmer air instead of colder. That's something we see, oftentimes in the summer on a cool night, we'll see a temperature inversion. Let's see here. So density altitude, though, takes into account that temperature, because cold air, this is an important point. Cold air is, well, I'll let you guys answer this since you guys are doing really well. Is cold air more dense or less dense? More dense than warm air, right? So cold air is more dense than warm air. Why do we know this? Okay, we can prove it, right? So anybody ever seen a hot air balloon ride or rise in the air? Yeah. Okay, so just think of hot air balloon. The reason why a hot air balloon rises is because the air inside the balloon is hot. It's warmer than the surrounding air, and so the balloon rises. Okay, so hot air is less dense. Now, this is something you can, a lot of times you'll hear people in the summertime saying, "Oh, it's so hot and muggy out. The air is so heavy." That's not a correct statement. The air is actually extremely thin, and that's why they're having a hard time breathing. You can correct your friends when they tell you this. Oh, the air is so heavy on a hot, humid day. It's not. It's very thin on a hot, humid day for two reasons. Number one, it's hot. The other thing is humid air has even less particles in it, so it's less dense. Humid air is actually less dense than dry air. So if you have a hot, humid day, the air outside is going to feel like it's maybe like 4,000 or 5,000 feet altitude. If you were to climb up 4,000 or 5,000 feet altitude, So all that stuff I just described to you is kind of relates back to density altitude. Density altitude takes all of this stuff into account, right? It takes the temperature and the pressure, and it puts them together to give you roughly what an altitude is, what it feels like outside for your plane and for you. So for if you ever want to, you can go on to several different aviation websites. We've got it in the SIA learning site. And you can look at some of the weather reports from all the different airports in the state of Wisconsin. We've got hundreds of them, but there's these weather reporting stations, and they'll report the altimeter setting, which is your atmospheric pressure, and it'll also report your temperature. But then sometimes they will, in the summertime, they'll include a density altitude. So it'll say density altitude is 4,000 or 3,000. So on a hot, humid day in summertime, you will oftentimes see density altitudes of around 3,500 to 4,000 feet. What that's telling you is the plane is going to act as though it's flying at that altitude at 3,500 feet, whatever, 4,000 feet. That's important to us because the plane does not perform as well at higher altitudes. You can still fly up there and it'll fly fine, but it's not going to perform as well. And why is that an important point? Well, when you take off, you need what under the wings to provide lift? You need air. Yeah, absolutely. If you don't have enough air, it's not going to produce enough lift on the wings to get the airplane to climb. And there have been a number of accidents and incidents where pilots have taken off where there was a high density altitude, like out west. This happens a lot, where the pilots take off. They try to climb, but the plane just won't do it, and they wind up going off the end of the runway and landing in a farmer's field someplace because they didn't take density altitude into consideration. Again, if you don't understand all that, it's not the end of the world. We're going to work on this later on. We get into performance and then some of the weather theory here. So, okay. All right, we talked about that. Yeah, moisture. Okay, so we talked about moisture. Dry air is heavier, is denser than humid air. Again, big concept. You need to understand that. And again, you can tell your friends when they say the air is hot, it's really heavy today. It's not. It's very light, and that's why you're having a hard time breathing in the summer. Okay, so now let's talk about production of lift. This is on page 4.5. So there are several different laws that we kind of go by in aviation that help us understand lift. So on 4.5 toward the end there, so Newton's, we'll talk about these one at a time. Newton's first law, every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. Okay, so this little plane right here, I'm just going to put it like right here. I'm just going to set it right there. Okay, that's demonstrating. Can you guys see that? Just, I put it right there. It's just demonstrating Newton's first law. There's no forces acting on it. It's not going to move. It's just sitting there. You've got, it's if now if I push it, I've got a force on it. I'm pushing right here. That's demonstrating, Newton's third law. For every action, there's an equal and opposite reaction. So I'm pushing on it, and therefore it's, pushing the aircraft. All right. So, but the first law is every object that persists in a state of rest or uniform motion in a straight line unless it's compelled to change that state by forces pressed on it. You can read that as much as you want. We don't really talk about that too much in aviation, just because planes move, and they generally we're not so concerned about them being on the ground. We're more concerned about what happens to the aircraft when it's in the air. So again, if an object is at rest, it tends to stay at rest. If I throw the plane, this is part of Newton's first law here. If I throw it, it's going to, there's forces acting on it, gravity, and it's going to cause the plane to do kind of an arc like that. All right, so that's demonstrating a little bit of it. It's going to basically follow that line. It's not going to deviate over this way because there's no other forces acting on it other than gravity. Throw it, and it's going to follow a nice little arc down the ground. Okay. So again, their description, this means that nothing starts or stops moving until some outside force causes it to do so. That basic common sense there. Newton's second law, force is equal to the change in the momentum per change in time. So for a constant mass, force equals mass times acceleration. Again, we don't talk about this too much in aviation, but we'll deal with this. So let's, this is on the next page here. When a body is acted upon by a constant force, its resulting acceleration is inversely proportional to the mass of the body and is directly proportional to the force applied to it. So in other words, if I take a, if I put a lot of force into this and throw it, it's going to go a lot faster as opposed to if I just drop it. Okay, there's, I'm putting more force into it. It's got mass. If it's got lots of mass, if it's like a bowling ball and I throw it, it's going to have a lot of force. Okay, but in this case, again, we don't really use this too much in aviation. We talk about it maybe a little bit with like stalls and things like that. So the other types of maneuvers, just because mass is an important part of aviation. If you're flying a really heavy aircraft, it's going to behave differently than like a Cessna 172 or something like that. It's, there's slight differences there. So the big one though is Newton's third law, and this one definitely want to understand. For every action, there is an equal and opposite reaction. So you remember that we talked about this a couple of weeks back. You stick your hand out your car window and you hold it up like this. You've got the action of the air hitting that, and then the reaction is your hand kind of moving back and maybe up a little bit, right? That's the Newton's law is stating basically for every action there's air hitting it. That's the action. The reaction is your hand going up or moving back. That is essentially what helps us get the airplane into the air. Newton's third law. And then there's also another principle that we need to talk about, that is Bernoulli's principle. So in the simplest way to demonstrate Bernoulli's, let's discuss what Bernoulli's principle is. So it's it states, let's see, the faster a fluid moves, let's see, well, actually, again, pressure. Okay, so pressure of moving fluid, liquid or gas, varies with its speed. I want to get this right. Okay, Bernoulli's principle states that as the velocity of a moving fluid, a liquid or gas, air, whatever, increases, the pressure within the fluid decreases. Right now, I'm applying pressure to this sheet of paper, okay? So there's relatively high pressure on the bottom and relatively low pressure up here. What Bernoulli said was if I create a flow of air across this sheet of paper, something should happen to it. There should be lower pressure up here. And because there's lower pressure, there should be relatively high pressure below it, right? Okay, so if I blow over this, we're creating a faster moving fluid, and Bernoulli said if you create a faster moving fluid, the pressure is going to be lower. Okay, that's what Bernoulli said. All right, so let's just demonstrate this. So I'm going to try to blow on this as hard as I can. Sometimes it works, sometimes it doesn't. It depends on the sheet of paper. But if I blow over this, what should happen to this tip of paper right here? Should it go up or down? It should go up if I blow hard enough on it. So let's see. Let's try once. Okay, did you see that? How the paper rolls there? That was Bernoulli at work. Okay, that's not Newton. That is strictly Bernoulli. So the faster, again, the fluid moves over that surface, the lower the pressure on this side of it, and the relative high pressure is going to cause it to rise. What you just saw there was basically what now we know as pilots what causes a wing to fly, and it's creating lift, along with Newton. Okay, there's two principles there, Newton and Bernoulli. Just as a side with that, you could walk into any FBO like this and ask pilots what makes a plane fly. Is it Newton or is it Bernoulli? And you're going to get two totally different answers. Some will argue on it. It's definitely Bernoulli, or it's definitely Newton, or it's both, but it's based on these conditions or something like that. That's something that is still debated to this date. Who produces the most lift? Is it Newton's principle, or Newton's law, or is it third law, that is, or Bernoulli? And it really, my answer to it is it really depends on the condition of the aircraft. And again, we haven't gotten into this. We're going to do this next session, next hour. We're going to talk about angle of attack. And I think it depends a lot on the angle of attack of the aircraft. But anyway, we'll talk about that in a minute. So again, that's those two concepts right there. Definitely want to understand that for the test, for the exam. And also to be a good pilot, you need to understand that because, without these basic principles here, you could make decisions as far as flying that are not in your best interest. You need to understand that. So, all right. So let's move on to airfoil design. So let's go here. All right. So there are different shapes of airfoils. I think they got it down here. Let's see, what is that? Yeah, here's some different shapes airfoils. This is in your book, by the way. You don't really need to dive too much into this. You're not going to see this on the test. Just know that this Clark Y airfoil, this is something that, and this is a cross section of the wing. It's basically, if you're looking at it this way, there's a kind of a curve or camber to the top of the wing. That's what we're seeing right here. This is a cross section of that wing right there. This is what a lot of general aviation aircraft, particularly the Cessnas, like the high wing aircraft, you're going to see this on the bottom of the wing. It's going to be relatively flat like it is right here. And then on the top, this is called the camber. That curve is called the camber of the wing. See how it's curved like that? And the cool part about this, let's go back here. There we go. So there's your camber right there. And you've got a lower camber, a little bit flatter on this side. Notice that it starts right here, but see how there's a real large curve right here and a low curve right there. Okay. So now we need to understand some terms here. We need to make sure this is, if you write down anything, definitely write this down. We need to understand this. So there is camber, and that's this upper portion right here. That's a term you should understand. That's the upper camber, and then you've got the lower camber. And in a lot of cases, like Cessnas, again, there is no lower camber. It's just basically a straight line going across. And some Pipers, like in my twin Comanche, it's got a lower camber as well as an upper camber. The Rocket Chief that I have is totally flat. There's no curve to it at all on it. So different forms of wings, but they both have an upper and lower camber. It's just that the Chief doesn't have much of a camber on the bottom. All right. So these other terms right here, chord, that's a term you're going to hear a lot, and you need to understand what it means. The chord is it's drawn from the leading edge of the airfoil, the very tip of the airfoil, all the way across to the trailing edge right there. So let's switch over to our plane here. Let's do it here. Right, so oops. All right, so it's kind of hard to see. I'm going to try to zoom into this. It's tough to see here, but there is a curve, an upper camber to this Cessna right here. If I do it like this, you can kind of see these. See, there's kind of a curve to that upper portion there. So it is. There's like a smooth curve there. Let me just draw that out here so you can see it. Okay, so it's just, that's the upper camber right there that we're seeing. And see how straight the bottom is right here? That's the lower camber. There's the leading edge, all right? So we've got our upper camber and we've got a lower camber. And then let's draw our chord line. So the chord line is from the leading edge, the tip right here, to the trailing edge. That right there is the chord line. From the trailing edge to the leading edge. And again, very tip of the wing. Does everybody understand that? That's a very important concept. You definitely want to understand. We're going to use this a lot, especially in the next chapter. So that's our chord line there, right? And then the mean camber. Let's go back to our mean camber is just the average camber throughout the wing itself. So this is the mean camber. We don't talk too much about that. in aviation, it's usually we're concerned about the upper, but you may hear that term used, every now and then. Mean camber. It's just the average distance between the top at any one point to the bottom of the wing, that cross section there. So we can see this distance from here to here is the same distance as from here to here. And same with this, here to here, same distances from here to here. That's the mean camber, or the average camber of the wing cross section here. So does everybody understand that? Leading edge of the wing, trailing edge, this is where we're going to see flaps, the ailerons, things like that over here. Okay. Okay. And then, so while we've got this, let's go here. All right. So here's air flowing over a symmetric airfoil. This is a, let's show this in here. Yeah. Okay. There we've got a little bit of Newton in here. We've got for a reaction, this equal opposite reaction. We've got this big, wing hanging out here. So Newton is when the air hits this wing is resisting it. That's our drag. That's basically drag produced by the aircraft, or airframe drag. So let's take a look at, this is turbulent flow. So this, if you were to take a golf ball, for instance, and put it in the flow of air, you're not going to see this, by the way. These diagrams are not in the books, by the way. But if you've got air flowing toward a golf ball or basketball or anything, what happens is the air will try to stick to it, but eventually it just can't stick, and it produces kind of a turbulent flow of the air. So you get these little eddies. We call these eddies right here. So you get this turbulent flow. That's another form of drag. We're going to discuss that later on as well. So let's look at it in terms of an aviation wing. So this is a wing, let's say, from our Cessna 172 that we have. So we've got air flowing over the top of the surface right here, and this is where it starts separating here. We can see these little eddies starting to form. What happens is, as the angle of attack, I haven't introduced that yet. We're going to talk about that in a minute. But as the angle of attack of the aircraft starts increasing, if the plane is flying in this direction, for instance, increase that angle of attack, that these little eddies right here start creeping up the surface of the wing, and eventually they get all the way to the top here, and they produce a stall. Don't worry about it. We're going to get into it when we talk about stalls a little bit more. We're just kind of introducing it here. All right. So this is a vector diagram of lift versus drag. Again, we know that anytime you produce lift, there is going to be some drag that's produced. In this case, you've got air flowing across this wing right here. It's producing some amount of lift because of Bernoulli's law. Here, you've got some air moving over the top of this. It's producing a little lift, but it's also producing a little bit of drag here. So let's go down and just bounce to another one here. I think I've got them in your book. So this is in your book right here. So this is on page 4-8. As air flows over a surface, let's use this right here. So as air flows over this surface right here, you'll notice, let's actually do this. Let's draw that. So if I got air flowing this way, let's say we got two molecules, one that starts here and one that starts here, and they're both flowing across the wing itself. You're going to find that this one that's going over this curved area is actually going a little bit faster on the top part. And because it's moving faster, it's producing what, higher or lower pressure? Lower pressure, definitely. Okay. There's been discussion in the past about if you actually theoretically had two particles that you could measure, and you let both of them go at the same time in front of an airfoil, would the one on the top, does it have to arrive at this point at the same time as the one on the bottom? And what they found was that the one on the bottom arrives here first, but the one on the top still travels faster. So it's producing lower pressure on the top. So we've got lower pressure up here, and it's causing that wing to get sucked up. It's actually lower pressure, just like a vacuum. It's sucking the aircraft up, or it's producing lift. Whereas down here, you've got higher pressure, so it's going to cause it to rise. Okay. All right. So now let's get into this a little bit more. I'm going to introduce one more concept to you, and then we're going to take a break. And that is angle of attack. Let's see if it's that. All right. So the angle of attack. Let me bear with me a second, guys. I can see if we can back up for a second. And I'm going to go off the book here because they do some of these things a little out of order. There's a term called flight path in aviation that we use a lot. And the flight path is the path that the aircraft is moving in. Okay. So in this case, I'm flying my Cessna like this, where the flight path is like this. That's our flight path. Okay. And I know the flight path is that way because I'm moving it in that direction, and you can see it. That's our flight path. I'm going to use my pen here. So our flight path is like this. So what's the flight path of this aircraft? Down. Yep, that's our flight path right there. It's down, going down. Okay. What about this one? Yeah, so the flight path is that way. Generally, when we fly with the airplane going forward. But you've seen aerobatic, pilots, they do all kinds of crazy stuff. The flight path may be like that for some of them. Or if you're not controlling your airplane very well, your flight path may be down like that. so the flight path is the direction the aircraft is moving in. So you need to know what the direction of the aircraft is moving in to know what the flight path is. And that path is aligned at that particular instant of whatever. So remember we talked about chord line, right? Chord line, what's the chord line again? Anybody remember the definition for that? Trailing edge and the leading edge. Yeah, perfect. The leading edge and the trailing edge, it's a line. So here's our flight path right here, right? Okay. And we've got our chord line, which is, let's see if I can use the it's going to be difficult. I'll show you on the screen here. So I'm going to put this on the plane. There's our chord line right there. There's our flight path. This right here is our angle of attack right there. So the green or that green and black pen is representing the chord line, and our flight path is this black pen. This right here is our angle of attack. That's the angle between those two lines right there. This is a super critical point to remember. Angle of attack is the difference in degrees between your chord line and the flight path of the plane. All right, let's take a break. We'll take about 10 minutes. We'll come back in and we'll dive into the second portion. We may not get the whole section done, but we'll dive into this. So that I presented a ton of stuff to you guys. So take a stretch, relax. If you guys have questions, fire away. I'm right here. So. All right. Expensive. I think that's
Yes.
Travis, did you by chance say Travis? Did you by chance watch the new live stream? By chance?
I don't know.
Not but
Yes, you can post
all right, everybody back? Do you guys remember the four forces of flight? What's this one right here?
Rust.
Rust, okay. What's this?
Wait.
Okay. Yeah,
Right.
got it. Okay. Here's a trick question for you. What's the flight path of this aircraft? Nowhere, right? There is no flight path because the plane is not moving. You need to determine flight path that the aircraft has to be moving in some direction. And usually when we refer to flight path, we refer to when we're talking about the plane while it's in the air. On the ground, it's always going to be on the ground moving around. And so the aerodynamic characteristics are going to be different on the ground than they are in the air. So let's get this plane up in the air, and then we're going to demonstrate some more concepts here. So let's switch this back here. And let's see. This is Reedsburg, by the way. So this is a 172. I'm not too good with these sticks here. Well, we're here now, so let's pause it right there. Okay, let's go outside. So here's our plane. All right. So I can show actually on here the flight path. So let's take a look at this right here. Let's actually do replay here. So I'm just going to move it back just so you can see. Oops, it was too fast. So we can see the flight path of the aircraft, that big magenta line there. That's the flight path of the aircraft. Let me draw that out so you can see it a little easier here. So our flight path is from here to here. Okay. Okay. Does that make sense? It's our flight path. The plane, it makes sense that it's going in that direction. So what we want to do here is, I'm just going to go here, and we want to talk about angle of attack a little bit. So we determine our flight path for the aircraft. The angle of attack, again, is what are the two things we need for angle of attack? You need, okay, so say one more time. Chord line and flight path. Always chord line, flight path. And it's not heading. It's not direction of the aircraft. It's always the flight path of the airplane. And the FAA will try to confuse you on that. They'll have some trick questions on there. So the thing that you have to remember is that it's the chord line and the flight path of the aircraft. So let's draw a line from the leading edge of this airfoil to the trailing edge. And I'm just going to extend this to the flight path here so we can actually see that. Okay, that line is kind of intersecting our leading edge and our trailing edge. It's not perfect, but it'll work. Let's just extend this a little bit more here. Okay, this right here is our angle of attack right there. That angle that's right there, or basically right here. That's the same number of degrees as it is all through all that. So that's our angle of attack. And in most aircraft taking off, they're probably going to be between 10 to 15 degrees, maybe a little less than that for angle of attack. The thing that you need to know is, no, actually, let's back up here. So there is, let's talk about a couple terms here. So we've talked about flight path. We know what that is. That's the path the plane is going in. In this case, it's going in this direction right here. Okay, that's our flight path. There's another term that you're going to hear a lot, and that's called the relative wind. The relative wind is just the opposite of flight path. So it's parallel to it. It's always, the relative wind is always parallel to the flight path, but it's in the opposite direction. It's the wind as the plane sees it. So if I'm walking on a sidewalk, right, or if I'm just standing on a sidewalk, I don't feel any breeze. There's no wind or anything like that. Let's say I'm just standing there. I'm not going to feel any wind on my face. But if I start running really fast, I'm going to feel a relative wind hitting my face. It's like it's like almost like a gentle breeze. I go run 15 miles an hour, which would be really fast for me, or anybody, I guess. But it would be, I would feel a 15-mile-an-hour breeze across my face. That's relative wind. So the relative wind is always relative to how fast the plane is moving, and it's usually it's always opposite of the flight path. That's a very important concept. Yes.
Relative would be just the opposite of your speed, or
No, it could change. It's if your plane's moving at 100 knots. So what you're saying is if your plane is moving at 100 knots, the relative wind would be 100 knots in that direction. Is that what you're saying? In a perfect atmosphere, if there was no wind at all, then yes, that would be true. But the problem is when you get up in the air, there's air currents that push the plane up and down. There's air currents that push it back, whatever. So you're in this air mass it's like if you would actually see an air mass, even on a relatively calm day, you would see little bubbles. If you could actually see air, you'd see bubbles of air rising. They would be, like almost like a boiling pot. Now, in a thunderstorm, if you're actually able to see that, you can to a certain extent. It's amazing if you've ever been close to a thunderstorm. If you've seen just an isolated thunderstorm as it builds, you'll see billowing towers of cumulus clouds or moisture moving up. So those are essentially, that's what's happening in the atmosphere. But in a perfectly calm atmosphere, it would be harder to see some of that stuff. It's bubbles or whatever. But so to answer your question, it would be if the atmosphere was totally still. But we generally always refer to it in relation to the aircraft. So the relative wind is going to be opposite. We don't care really about the speed of it. The relative wind, we can look at our airspeed indicator or get an indication from the aircraft. Just by listening to the wind across the wings, we get an idea of how much wind is flowing across them. Okay, so that's relative wind. Flight path, parallel to it, and opposite is a relative wind. Two very important concepts. Okay, and then let's see here. We talked about thrust and drag. So thrust makes the aircraft go forward, and drag is going to fight that. It's going to resist it. So here, what we're seeing, though, let's take a look at this. Here. So let's look at Bernoulli for one thing. Well, let's look at Newton's third law. We know that Newton's third law, for every action, there is an equal and opposite reaction. So here's what's happening with Newton. So air comes across the plane. We've got an angle of attack here. We said, let's do this here. So our angle of attack is from here to here. There's our angle of attack right there. There's the magenta line, that pink line right there is our flight path. So that's our angle of attack. So here's Newton coming along. And it hits this surface, the lower surface of the wing, and it causes there to be an opposite and equal reaction. So the air is kind of getting pushed down as it hits that. It's what we call downwash. It hits the air hits that bottom portion of the wing, it's pushing it down. Bernoulli, at the same time, is also producing lift up here on the top part of that curved surface. So let me see if I can draw this. So we've got this curved line on the top here. That's that camber that I was talking about. So air comes along the top here. There's Bernoulli now at work. The air hits the leading edge and goes across the top. It's got to travel really fast to kind of catch up to the air at the bottom. It doesn't meet up with it, but it'll travel faster. Because it's traveling faster, we're getting less pressure up here, which translates to lift. So now we've got lift from Bernoulli and from Newton. This is probably one of the concepts that even pilots, there's a lot of pilots I know that don't understand these basic concepts. If you can get this, if you understand this stuff now, I guarantee your career in aviation is going to be a lot easier because you'll know what produces lift, what's causing, whether it's Newton or Bernoulli. And if you go to aeronautical engineering, this is stuff is, absolutely required. They have there. So, all right. So let's get into. they do talk about critical angle of attack. So there is a on page 5.3, there is what's called a critical angle of attack. And every aircraft is going to have what's called a critical angle of attack. And what happens is that's the point at which the plane cannot, the wing cannot produce sufficient lift to keep it in the air. And can anybody guess what happens then? Yeah, the plane is going to stall. It's not the engine. You hear like news media, they always get this wrong. I don't know why, but well, I shouldn't say always, but sometimes they get it wrong. They'll say a plane stalled, and it's implied that like the engine stalled. It wasn't. That's not the case. When we talk about airplane stalls, we're talking about the wings stalling. They're not producing sufficient lift, so they stop. Keep the airplane at that altitude. What happens is you're flying along, you increase your angle of attack like this, and the plane just basically starts descending. It doesn't just drop out of the air. The first time I went up, I did not understand it. I thought when the instructor told me, yeah, we're going to do a stall, I thought the plane was literally going to fall out of the air. It's like, okay, we're going to probably crash, but I don't know. We wound up staying up in the air. It was just a very gentle maneuver. So basically, the plane basically points down. Like every now and then, wing may drop like this, a little bit like that. It's nothing serious. You just correct it. What all you have to do to get out of a stall is well, I'll let you guys decide because you guys are figuring this stuff out really quick. How would you get out of a stall if let's say I'm right here? What would I do to reduce my chances of getting in a stall? Yep. I think everybody said it. Yep. The first thing you can do right off the bat, if you got altitude, pitch the nose down. Just push the control yoke. It doesn't have to be aggressive. There is such a thing as a negative stall. You can actually push it so aggressively that the plane stalls in that direction. So I mean, that would be an extreme, but it is possible. So you want to basically do a very gentle, just relax. Oftentimes, I guess you just let it go over the control yoke, and what will happen is the plane will correct itself. It'll just fly out. If you've got it on a trim, it may not, but generally speaking, if you just let go of the control yoke, the plane is just going to fly out itself because it wants to see that little room there. Okay, so that's what we call a critical angle of attack, and every plane has it. The critical angle of attack for most airplanes is between, could be as low as 15 degrees. This angle right here, let's actually put all this stuff up here. So let's draw this again here. So again, this is our flight path right here. One there, and our again chord line is from the leading edge to the trailing edge. I'm going to draw that. So goes through the trailing edge there. There's our angle of attack right there. Okay, so you can see it. That right there is our angle of attack. So the critical angle of attack for most planes is around anywhere from 15 to 18 degrees. In most Cessnas, I think it's around 17. Don't quote me on that, but I think it's around 17 degrees. So let's test this out. Let's actually do a stall in this plane. So I'm going to do something that I would never do in real life, and that's a low altitude stall. Yeah. If we were up flying, there's no way I would do something like this. But because this is a simulator, and it's so of course I could probably just raise the altitude, but for the sake of the class, I just want to get you guys, so you can see what's happening here. So let's go ahead and clear all this stuff off here, and I'm going to. Let's go. All right, so there we go. Let's, there we go. All right, so we're climbing here. Gotta make sure still climb. All right, so this is actually, I'm going to switch back to my view here. Oops, that's healthy here. All right, so we're going to get into a climb here. I get it up nice and high. And what I want you to do is look at the, we're actually probably in a stall right now. Let's pause it here. Okay, so we're actually, I can tell we're stalling the plane right now. And the reason I can tell is because the plane is descending. I've got my nose up. So let's take a look at this. This is a good example here. So it looks as though, if I were just to see this airplane, it looks as though it's flying, right? But look at the flight path right here. You can see right here, our flight path is going down, but yet my plane is pointing up. So that's the direction of the aircraft that is flying right there. So let's do our chord line thing here. So there's our blue line right here is the flight path. It's right here. It's one here. Okay. And let's take a look there. Now you can really see it. Okay. So there's the leading edge right there. We'll do the chord line, tip of the edge, the wing to the trailing edge. And look at how much more steep that angle of attack is there. You see how much of a difference that was from what we had before? It's a much steeper. So that's probably closer to 8%. And look at the flight path. So our plane now is what's happening. If you're actually able to see the air as it flows, the air comes over like this. What's happening is it's hitting this edge, it's coming up, but it separates and it creates these like eddies right here. There's in the materials, the SIA materials, online learning, there's some really good videos of where they taped string on the surface. And I think this is University of North Dakota. I think it was there. I can't remember. It was one of the aviation universities. But what they did was they put yarn. They taped it onto little strips of yarn onto the wing, and they demonstrated physically. They showed what happens in a stall when the plane, is going like this. And what we did here, this flight here, where I was climbing, but I was too steep, and so the plane started descending like this. Now it's in a stall essentially, and it's coming down, and we can see it because we're losing altitude here. I've got the nose really high, pitched up, but it's not flying. It's descending. It's it's still flying, I should say, but it's instead of climbing. You'd think a plane that's pointed up at the sky would fly. No, it's going too slow. In this case, the wing can't produce sufficient lift, so it's actually descending like this, even though our nose is up. That's why we have to understand chord line, flight path, and things. So, Jonah, I'll get to you this.
In that situation, when you're super low to the ground,
this would be a mistake on the pilot's part. I mean, right now, there's not much room for me to work with. So there are a couple terms that we use a lot. Altitude is life and speed is life when it comes to aviation. And you'll hear military pilots say that. I'm sure you've heard your dad mention that. Altitude and speed are life, with flying any aircraft. So in this case, our airspeed is way too low. If you look at the let's just switch over to the inside cockpit there. So here's our airspeed. It gets kind of dark there. I don't know if you can read that. Yeah, it's really dark. So this right here is the white arc, and we're below the white arc right now. We're at like 40 knots there. And I wish I could make that brighter. Can't really. This right here, this little. Can you see the white arc right there? That barely, yeah, it's just barely there. But needle is right there. That's the needle right there. So it's actually we're in a stall right now. So that you can't always tell that you're in a stall just by looking at the airspeed indicator, because you can really stall the airplane at any altitude, pitch attitude like this. This is what we call attitude. This is the direction the aircraft is pointing. And you can install it, at any airspeed. But in this case, let's go back to here. Let's do this. Okay. It's close there. Donnie, you had a question?
I was going to ask if this is less treacherous for a tail dragger than it would be for a trike, because for trike CP, dragging the tail looks like this.
That's a good question. It's a minor point at this point with the plane. If you're, whether it's a tricycle gear or a tail dragger, the nose is dragging, creating more drag out here, and a tail drag will be producing less drag. Generally speaking, they made like Cessna 172s that actually had a tail wheel on it called a 170. It's basically the same plane, but it had a tail on it. And then those pilots will tell you that those planes stall at a slightly smaller or slower speed. So it's probably, a tricycle gear is probably not going to be as good for you, but it's minor. It's something that you wouldn't even think about. So they mentioned the same thing there. So to get out of this, we have to do one of two things. Okay, so Jonah brought it up. You know, we can, what are the things that we can do?
Because we're still near the runway. If there was no runway, just like that.
We could try to land it now. Yeah. If I, what I want to do in this case, you definitely, in a stall, you want to be careful that you don't drop a wing, because there's a danger at this point of going into a spin. When you get into a stall, you have to make sure that your rudder is coordinated right. We're going to get into this a little more later on too. But when you come in, you want to make sure that your plane is, you know, as coordinated as possible. That's keeping the rudder. Basically, the ball is, and I'm throwing stuff at you guys haven't learned yet, but there's a device called an inclinometer on here, and all it is just a tube. It's a curved tube, and there's a ball in the center of it. It's like a level. If you've ever seen a level, somebody using a level, if you've used it in woodworking, we use that to measure how level something is. It's the exact same concept. It just tells us where the center of gravity is. So if I have, you know, too much rudder in there, that ball is going to be swung over to one side or the other. And that's when you have the potential of getting into a spin. Don't worry about it, because we're going to get into spins later on. Right now, we're just, in this case, we want to get this pilot out of this situation. So the things we can do, what are the options that we have to get this guy out of this condition? Pitch down.
As if you decrease like the time and then that's like your
Yeah. Yeah. So those are both good answers. Those exactly are what the FAA is looking for. And the case of the power, I've got it at max power right now, which is crazy. You know, you'd think, okay, well, it's got lots of power, I should be able to climb. Now, if I was in a jet, a fighter jet, yeah, I would just, you know, put in the afterburner and just climb straight up. But unfortunately, with a small general aviation plane like this 172, they only have so much thrust. And so they can't produce enough thrust to fly out of a stall. So if I had it, I would definitely want to put in the best bang for the buck is the stick. I want to actually change the pitch of the aircraft and decrease that angle of attack. So I want to bring that angle of attack from here down to here. I'm going to get it, decrease it. That'll get air flowing over this portion right here, and then we'll be able to fly. So let's test our theory out here, and hopefully we won't crash. So let's go ahead and clear this out. And let's see, let's switch back here. All right, so there we are. We've got a lot of altitude. If I crash here, this will be really embarrassing, but it's possible. So all right, so what I'm going to do, the first thing I'm going to do, well, I can't do anything with the throttle, so I've got max throttle right now. But one thing I can do is lower that pitch, right? Okay, so are you all ready? Here's what's going to happen. I'm going to go ahead and pitch over. I'm going to unpause it. Okay, I'm going to pitch it down. Whoa, oh, yeah, okay, we damaged the plane. So I was too aggressive on the pitch down. So now this is a good lesson, because this kind of thing does happen to pilots, where they, you know, like in real life, the stall warning would be going off. You'd hear a warning saying, you know, the plane is coming close to a stall. I have the sound turned off here. And you'd hear like a horn going off, warning you that there is a stall. That's called an imminent stall. And in this case, I didn't hear it. I should have been watching my airspeed indicator, and I wasn't. So we'd probably walk away from this, but the plane would be a total mess. It would not be good. But this is the reason why we have to understand all those, the flight path, the angle of attack. We need to understand that stuff if we're going to fly a plane safely. And this is why we go through all this stuff and talk about it. So again, critical angle of attack, flight path, relative wind, all those terms we need to understand. Okay. All right. So let's go back. Let's go back and reset this flight. Here, does anybody want to see the review of that flight? Let's take a look at all this here. Yeah, it's going to be pretty nasty here. So, all right. So let's see what I did wrong here. So, I should get down. Lighten it a bit. So, don't think I can turn on the lights here. Did you see the airspeed indicator there?
Yeah.
Yeah.
Okay, let's watch that. this is again, terrible example. Like I said, if you guys can fly a simulator, you can easily fly a real plane. I find it so much easier flying a real plane than I can a simulator. It's pathetic. It's very smooth. Obviously, I don't fly like this in real life. Otherwise, nobody would fly with me. I wouldn't blame them at all. So, but like I said, the thing that's tough about a simulator is you can't feel the forces in the seat of your pants. You can't feel the shaking of the aircraft. You can't hear the noise of the air flowing over the wings in the cockpit. You hear that flowing noise. Those are all things that we use as pilots to help us indicate where we are in space and how the plane is operating. And you can't get that from a simulator. Kind of a little bit here and there, but it really is not the same thing. All right, so let's see how bad I did. So let's go here. Right here. So let's start. Let's do it in slow motion here. Let's do this.
That's the answers the actual.
Oh, gotcha. All right, so I want to go. All right. So I see. I had it paused here. I see. Yep. Thank you. Yeah, it would take. We got some rain there. Okay, that's cool. Short light. Here we go. All right, let's go right to here. All right, so now we're moving. So let's do it in slow motion. All right, so watch our airspeed indicator right here. We can see that. I'm just going to focus on that, and let's just see how bad I did when I took off. First off, whenever you apply power on a single engine aircraft, these again, we're going to get into this later on, but you can start studying this stuff. There's a force called torque. See how the plane is actually moving off to the left side there? It's called left turning tendency. And whenever you add full power to a plane, if you don't compensate with your rudder pedal, the plane is going to want to veer off to the left. And you'll notice it for new pilots, this happens all the time. And some experienced pilots, when they apply full power, the nose wants to drift left. There's 4 primary left turning tendencies for the plane. We'll get into them later.
Left tendencies like most noticeable and like conventional gear.
They're more dangerous in conventional gear, and yeah, to a certain extent, they are a little more noticeable because the angle of attack that the plane sits on the ground. So on the ground, it's sitting like this, whereas a tricycle gear is sitting like that. We'll get into that though. That's a good point to bring up. All right, so now I've got enough airspeed. See how my airspeed now? I'm in in the white arc there. I'm climbing, but now I'm getting into a real steep climb. Watch this airspeed indicator right here. So we're at. You really can't see that, can you? It's right now it's about 90. Something happened there. Speed dropped all of a sudden. It's a glitch. Right, so we're at 80 knots right now. That's 80. All right. And that's me just lowering the nose a little bit, but the airspeed's starting to fall off a little bit. It's at 70 right now, 70 knots. And our stall speed in this aircraft is 60. It's actually about 55 for the white arc. We don't have any flaps, so right now we're actually in a stall. There should be a stall warning light here someplace. Let me just pause a second here.
Isn't that red one?
Yeah.
What's that?
Above your number.
No, this is the ELT. That's it. ELT. Let me just see if I can get the. Let's see if this is. I don't know if it is, but let's see. Okay. Okay, those warnings there are all. Oh, that's our ELT that's going up. That little pew 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 sound. Can you hear that?
Oh, there's your stop.
Yep. So you can see there. So this and again, did you guys see where it actually? Let's go back up here a second here. So I'll do it in slow motion. So that's another thing I would have done is I would have checked my ELT. Okay, so you can see our airspeed is really low, and I can pull back as much as I want. Right now, I'm starting to pull back. Actually, let's do this. Okay, so let's do this again. Let's go here. Okay, so watch the control yoke. What I'm doing at the control yoke, there I'm trying to break the stall. We're losing lots of altitude, and now I'm pulling back to avoid the ground. Instinctively, I'm pulling back. I want to see if I can flare it. We obviously hit really hard, damage the nose. Again, we probably would walk away from that, but we wouldn't feel really good about it. So that little buzzing sound, that's the stall warning. I don't know if you can hear that from where you guys are there. There's like a buzzing sound. That's the stall indicator. Let's try this again. There's the little buzz right there. It is the stall. Okay. So can we, let's go back a little further. Okay. All right. So you can see I've got that control yoke so far back and it's in the stall now. Now I nose it over and we instantly lose all that altitude. So that it really didn't illustrate the point that I wanted to get across, was that when you decrease the angle of attack, you're going to produce more lift. In this case, we just ran out of altitude and airspeed. We just didn't have enough to save us. Normally, Max said, when you're flying, you do your stalls at like 3,000-4,000 feet. You're not going to do a stall below the ground intentionally. It's way too risky. So, okay. Does that help at all? Concepts there a little bit there. Does anybody have any questions on this stuff at all? Yeah.
How much do you think that repair cost would be? Because he slams like right into the engine.
I don't know. So, okay, it's a good question, and I will answer that because we probably have a little bit of time here yet. So, an engine is typically, depending on the type of aircraft engine, it's going to cost anywhere from bare minimum $20,000 to as much as you could, on a general aviation, you can spend up to $60,000 for a rebuild engine. So the prop has to be replaced. Because anytime there's what's called a prop strike, you have to replace the landing gear is damaged, skins. What's that?
Shock damage, definitely the same.
Yeah, airframe is going to have to be fully inspected. You'd be surprised what small planes can take. So I have a twin Comanche, and I bought it after a guy crashed it, which sounds really weird. Why would you want to buy a plane that was crashed? Well, the thing you need to understand about aircraft is that, like we learned in structures last week, they're made of aluminum, so you can fabricate aluminum in your own shop. So I took it to a mechanic. He was based here at Breezebury, he's now in Maryland, but he basically did all the work on it. He replaced all the skins on it, because what happened was the guy took off, and the door popped open. He probably was furious at himself for having this happen. So he took off, he brought the gear up, and the door popped open on the twin. His wife freaked out because she's not used to flying, and I've had this happen with pilots before. I've had it pop open before in flight, and it scares people, even pilots are a little startled by it. But if you know that it's not a big deal, you just continue flying. Well, what happened for him, he freaked out a little bit too, and so he said, okay, maybe I should land. He started coming down. He realized the gear wasn't down. He brought the gear down and then landed with the gear as it was coming down, and it just slid off the end of the runway. It didn't cause any fire or anything like that. So the belly was scraped up, the props were nicked, the engines obviously had to be torn down and rebuilt, and things like that. So there was some cost in it, but I got it for a really good deal, and the repair costs were very respectable. Yeah.
What was the cost of that before?
For that one, I think it was around 60,000 for well, maybe less than that. I think it was maybe like 40,000. No, 50. Yeah, because it was they had to repair both engines, new props. So yeah, and then the airframe was like 25 after that. Anytime a plane has been in an accident, it's not a bad idea to buy it then, depending on the condition of it. You have to have a mechanic look at it, but a lot of times they can fix it because again, it's just aluminum. They just form the aluminum, in their shop. They'll cut it there, they'll hatch it out. That's what they did with mine. You'd never know by looking at my plane that it was ever in an incident, any kind of accident or incident in flights.
Have someone who didn't sleep, have someone who accidentally crashed one of those planes on which we were a few years back.
Oh gosh, I remember there was a guy that went off the runway in a Cessna. I think it was a 180. Is that the one where you kind of should have landed?
Yeah, I think it was like a move.
Oh.
Any programs.
I don't know. Yeah. Cadence?
Do you know what happens to his license for that? Like, does he have to get like recertified or like what happens?
No, you know, the FAA, you'd think the FAA would really come down on pilots. Now, if it had been a mistake that endangered somebody else or it caused damage to property or something like that, the FAA probably would have investigated a little bit and said, yeah, you really need to do recurrent training or something like that. But in this case, it was just one of those cases where it could have happened to anybody. Nobody was hurt. Everybody walked away from it. So the FAA probably isn't too concerned about it. The FAA gets involved. The FAA, gets involved whenever there's certain types of injuries to people. They have to be severe enough so the FAA gets involved. Or if there's a death, or if there's a fire on the plane, even a small fire, you have to report that. So but oftentimes pilots don't even report the accidents. They have a minor accident. Like I've got another plane, a Cessna Skyline. It's kind of like this one right here. It hit a prop strike. So the guy was taxiing along and he hit a taxiway light. And whenever that happens, even though it was a plastic taxi light, but every time you have a prop strike where the prop hits something, you have to do full inspection, and that means tearing down everything. So the guy probably didn't report that, and something like that. And I doubt that I would report something like that. I really should, but it's the FAA is not going to do anything. There's no enforcement action. They're just going to say, oh well, for you're going to have to pay a ton of money, and that's it. But anytime there's an incident where somebody injury is involved, again, they have very specific. If you look at the federal aviation regulations, when they say injury, they actually have very specific terms that define injury. Like torn ligaments, broken bones. They're very specific on that. So obviously, if there's a fatality involved, then they want to get involved, and they could involve on that. So, or if you're endangering somebody on the ground, that's where the FAA says, yeah, we need to look at your license and see if you're really fit to fly or things like that. So the FAA strictly is looking at the safety of the public, the pilots, other pilots, and things like that. If that person poses risk, in this case, when the guy landed, he wasn't posing a risk to anybody, and it just damaged his plane, unfortunately. So, okay, let's see. So, okay, how do we control lift?
Wow.
Okay, so I hear flaps. Okay, I hear thrust. What else?
Angle of it.
Angle of attack. Yep, angle of attack, and yeah, and speed, definitely. Yep. So they all those things kind of tie together, right? So yeah, we can use angle of attack if we've got enough speed, we can use angle of attack to a certain point. But once we hit that critical angle of attack, we're not going to go any faster. I mean, it's the plane's going to start descending. You may have you have a high your plane may be pointed like this, but like we just saw in the demo there, the plane was actually descending like that. That was our flight path. It was down like this. So flaps definitely improve lift. Now let's get into that. Why do flaps increase lift? Let's see if I can do this here. Oh, I gotta start this for a little bit again.
Does the flaps angle leaving down?
Well,
sacrificing speed.
yeah, let me show you. Let's what's that?
But where is he again?
Oh yeah, that's that.
Yeah.
Yeah, change the page. Let's go here. Start the flight. Okay. Yeah, and actually that I don't know why that would have gone off, because it was going off before we actually landed, so crashed. All right, so let's take a look at the why when flaps come out, they produce more lift. Circle here. All right, first off, all right, I'm gonna have to take off again, right? Yeah, because we need to see it. So, sorry, I'm going to do this from the back. Some of you guys, if anybody's ever done remote flying, they probably can do this much better than I can, but I'm not really too good with this here. So see how the plane is kind of turning to the left there? See how it wants to turn to the left? I've actually got right rudder in it right now. See, it's really going off to the left there. I'm using to do the, it's just terrible. So, all right.
Are you controlling the letters with
By twisting the
oh,
control yoke there, which is not natural. It's like, all right. So
I think it's worth the $150.
What's that?
I think it's worth $150 for pedals at this point.
Yeah, it really does help. You'll find if you do have rudder pedals, they'll start getting you into the habit of using your feet. And it seems really weird, but if you fly enough, there is going to be a point, like if you do like a long day of flying, there's been days where I've flown literally 8 hours straight. And I got on the ground, got into a car, and I got confused between which foot to use for gas and brakes, because you're steering, the rudder pedals control that rudder. And so I'm used to doing that all the time, turning right, left, whatever. So when you do that enough, though, when you get to that point, then you understand how the rudders are working. But it took me a while to get there. So let's see. All right, so let's go here. All right. So we're talking about flaps now. So first off, let's take a look at our flight path here. So there's let me zoom up here. There's our flight path right there. You can see that behind us. So we know, let me just draw a line here so you can see the extend our flight path. So we know the flight path is like that. That's our flight path right there. Let's draw our chord line. Again, tip of the wing to trailing edge of the wing right there. So I just want to make sure that it extends it all the way down there. So there's our angle of attack. All right, so now what we want to do is we want to extend the flaps. I don't know if we can do it in pause mode. Okay. So this right here is, again, it's the tip of the wing to the trailing edge. This is, kind of gives you an idea of the present angle of attack that we have there. Okay. So now we continue on. So this, let's go back inside here and pause it. Actually, let me do this. Let's switch back here. I'm going to try to do this. This is a tough angle to fly from. All right, so I'm going to start bringing out our flaps here. So there's just, you can kind of see them dropping there. Their flaps dropping. All right. So now let's right there, and I'm going to pause this second. All right. So now let's take a look at our angle of attack. So here. So again, all we're really concerned with is the chord angle that in relation to the flight path. We don't really care that the plane is pointing up in the sky like this. We're really more concerned about the flight path and the chord line of the angle attacker. So let's go ahead and do this. So I'm going to just extend that flight path right there. And here's our flight path. And now let's take a look at where the angle of attack is there. So let's go here. Zoom in. So again, chord angle is what? Our chord on line is what?
Leading edge to
Trailing edge. All right. So let's do this. All right. So there's the leading edge right there. The trailing edge is no longer here. It's at the bottom of the flap. You see that? Okay. See how much of a steeper angle that we've got there? So now what's happening is there's several things going on here. We're creating more of a camber on the top of the surface of the plane. And because of that, the air has to move faster over the top. So we're producing more lift because of Bernoulli this way. We're also getting downwash from these flaps right here. Can you see that right there? Look at it real closely there. That flap right there. See how it's down there? So that's what's happening is air is coming across this way here. It's hitting this right here and it's bouncing down and creating downwash. But air that's hitting that flap is also creating downwash. It's going down like this. So we're actually producing a lot more lift here because of that flap being down there like that. We've changed the chord length. So that's, again, our angle of attack has shifted just by changing the flaps, adding the flaps in there. And now we're producing more lift. Because we're producing more lift, what's a byproduct of lift? Drag. Yeah, we're producing drag. Yeah. Okay. So anytime you produce lift, you're going to produce drag. It's part of life. All right. So now let's actually continue on and let's do a stall with the flaps on, just so we see. Maybe I can cover from this one. So let's go here. Looks pretty high, but notice that our airspeed, I don't know, can you see that there? There's the white arc right there. And then there's our needle right there, and it says that we're at about 60. This time, I should have no problem getting out of this. We're getting close to a stall here, but we're not actually stalling the aircraft. So let's try this time. This time I'm going to turn the yoke on. So watch what happens here. This down a little bit. All right. So I'm going to unpause it, and we're going to do what we tried to do before, and that was pitch the nose over and to break the stall. So let's do it again here. Here it is. Pitch the nose over. And, what's that? Well, now keep in mind that that's just a reference. You know, the plane can stall. I could get this plane to stall at, 70 miles an hour or 70 knots or 80 knots if I wanted to. That's just a reference. And that's an important concept. I'm glad you actually brought that up, Donnie, because a lot of people think that those stall numbers that are on the airspeed indicator are hard. As long as I stay away from those numbers, I'm safe, right? Not true. You can stall an aircraft. I'll demonstrate it here. So I'm going to do what's called an accelerated maneuver stall. So what we're going to do, I'm going to build up a little bit of speed here, and I'm going to get the plane to actually do a what's called an accelerated maneuver stall here. So watch what happens to the airspeed. I'm just going to bank it like this and then pull really hard. There's the stall right there. So now the plane is actually, did you hear the stall warning there? The plane actually stalled at, let's pause it here a second here. Let's replay that so you can see it. So that's why we don't always trust the airspeed indicator. It's not always a good indication. What's that? Yeah, the airspeed indicator is using the static pitot system, which is, again, I think we get into that in instruments and stuff like that. But let's see, let's back up a little bit here. Okay, so there's the stall warning right there. That's what we call an accelerated maneuver stall. Okay, so let's pause it and let's go forward here. All right. Flying, and now I go into a steep turn, pull back really aggressively, and there's this point the plane is, yeah, you can kind of see it stall there. But the airspeed was really high. If you watch the airspeed through that whole maneuver, it's actually stays pretty high. So again, that's why we don't, we use it as kind of a gauge. If you're flying normally, then you wouldn't have to worry about it.
This isn't just when you use the atmospheric pressure.
Yep.
Can't you also calibrate that for the
instrument? Yeah. That's there's several different types of airspeed that we talk about. And again, we'll get into that when we get into airplane instrumentation, but there's what's called, there's indicated airspeed. Anytime you hear the word indicated, it means what you're reading off the panel, okay? Indicated is what is indicated on a panel gauge or something like that. There's also calibrated. So in this case, there is such a thing as calibrated airspeed. And then there are, several different types of, you got, let's see, there's indicated airspeed, calibrated airspeed, the other ones. I know there's like two others that you'd use. Most of the time, you're just going off a calibrated airspeed. I'm sorry, indicated airspeed. You use calibrated airspeed when you're doing flight planning. If I'm flying a long distance, I need to figure out what my real airspeed is so I know how long it's going to take me to get something. So that's where we would use something like that. And we're out of time, guys. We did cover a lot today. Hopefully this is giving you kind of an idea of how some of this works. Can you see now why I want you guys to actually either fly in a plane right now or fly the simulator? Because this stuff will give you a chance to kind of, use the rudder pedals and get out of some of these situations that we're talking about. So for next week, then just plan on doing the rest of chapter 5, which is aerodynamic flight. There.
Thanks, Joe.
Yeah, thank you. Nice class, guys.
Today is the third, right?
Yes, it is. Yep.
I will not be here next week. What should I do?
Just watch the video. Yep.
All right.
Yep. And if you got
Will
questions,
that just be posted on the
Yep.
SIA website?
it'll always be on the first session there. So just
All right.
off here.
All right. Do I have to watch it live or is it like a recorded version?
Just watch the recorded version. Yeah.
All right.
And if you've got questions out, let me know. So
All right. Thank you. Thanks. So wouldn't the indicator speed moving forward if pressure is on?
if the pressure is lower, the indicated airspeed, I believe, is going to be higher. Because there's not, so as you go up in altitude, okay, and I think we get into this a little bit more later on, but as you go up in altitude, the air is what, less dense or more dense? Less dense. All right, so there's less particles hitting that pitot-static tube in there, and because of that, oh gosh,
The computer in the thing will think it's stalling.
yeah, it's actually a mechanism on older planes. It's actually, the computer would be the same thing, and they've got an air data computer that they use for it. So it's gonna seem as though, gosh, let's wait for me to answer that, and because I can give you a much better explanation for it when we actually go over that. It just, there are several factors that play into it. The wings, the airplane is going to actually be moving faster through the air. Okay, I'm going to think about this. So the indicated airspeed is going to be lower. Yes, you're right. But the actual airspeed of the airplane is going to be much faster. And that's because the air is less dense. And as it goes through the air, even though it's indicating a lower airspeed, it's going to be flying through the air much faster. Because there's less air, less molecules, less drag, and things like that. Okay.
Oh, I had a question about the airfoil design.
Yeah.
So is the airfoil design talking about this right here or the fuselage?
It's talking about the cross section of the wing
Right
itself. Yes,
Okay,
exactly.
okay.
So if
Because
you-
I was kind of getting confused because you were pointing right here. as
oh,
well as you were
sorry.
pointing
Yeah.
Right there, so I
Sorry.
was kind of
Yeah.
like,
Yeah.
and then I scheduled my medical certificate.
Excellent.
verification.
With the doctor and Dr. Anderson?
No.
You got another one?
Yes,
Okay.
I got another one, but still an pilot. Pretty cool. But
Excellent. Excellent.
it's on Friday. So,
Excellent. Excellent.
yeah.
Good.
Mhm.
Yeah. It wasn't Dr. Hoffman, was it?
I'm not sure.
Yeah.
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 I'll have to check up his name or something.
Yeah.
but
Is it Mile Bluff Clinic you go to, or is it not a medicine?
I think it's down in Madison.
Yeah. Okay. Yeah. There are a bunch of them, and actually, Cadence, if you don't mind, if you could send me his contact or her contact information, just so I've got it on record. Let's see. I'm gonna turn this off. Then